Here I'm going to walk you through the investigation for binomial expansion. Maybe in the past you've talked in your math classes about how binomials squared or cubed are related to areas and volumes of shapes or solids. So here we're going to put that to work. So I have a rectangle or a square here, a square I guess. I have a square here, and the square is the dimension p plus q wide and long. Okay, so here I have p plus q added together. Here I have p and q separately, but basically the side of each side of the square is p plus q, right? So what is the area of a square if one of the sides is p plus q? It's going to be p plus q squared, right? Now let's try to find the area of the square with an alternative formula. What if we divided it up into 4 boxes like we have here? We're going to have box 1, box 2, box 3, and box 4. Okay, so we're going to divide it up in these 4 boxes, and we're going to use the side lengths p and q to calculate the area of each one of these boxes. For example, this small box, box 1, it's p on each side. It's a square, right? So this is going to be p squared. And what do you know? Box 1 has area p squared. What about this pink box here? Its side length is q, and it also has a this side is equal to p, and this is q. So the pink box is actually p times q, right? What about box 3? It also is p times q, isn't it? What about box 4? Box 4 is q and q. It's q squared. Now, what if we totaled these up? What are we going to get? We're going to get p squared plus q squared, and then the pq and the pq can be added together, so we get 2pq. That should look kind of familiar. Find an expression for the volume of the cube considering each side is p plus q long. Now, instead of having a square that's divided into 2 rectangles and 2 squares, now we have a cube. It looks like a Rubik's Cube, doesn't it? It's almost like a Rubik's Cube. If we divide it up into these 8 sections, can we figure out the volume of each one from p and q? Yeah, I think we can. So, like for example, these short side lengths are all p. So this is p, and the longer lengths are q. Okay, so let's see. Box 1 is a cube with side p, so it's p cubed, right? What about box 8 back here? Box 8 is also a cube. Each side is length q, so box 8 would be cubed. What about box 2? Box 2 is like a rectangular prism, and look like these 2 short sides are p times p. The length is q, so actually what we got is p squared q. And box 3 and 4 all look the same, don't they? They're all p squared q. Box 3 and 4 are also p squared q. What about box 5? Box 5 is also kind of a rectangular prism. It has 2 sides that are q and q, and it's got a depth which is p. So it's instead of p squared q, it's pq squared. 6 and 7 are also same shape. So pq squared and pq squared. Now if we're going to add these up, do you see that these 3 are the same? And maybe these 3 are also the same? So when we total these up, we're going to get p cubed, q cubed, and in the middle we're going to add up those 3. We're going to get 3p squared q plus 3pq squared. That should look familiar too. Okay, the binomial expansion of a plus b squared is a squared plus 2ab plus b squared. do you see how the coefficients here, and you may not be able to see the coefficients because you're like, there is no coefficient here. There is no coefficient here. But remember that when there is no coefficient, that means the coefficient is 1. So the coefficients we have here are 1, 2, 1. 1, 2, 1. Okay, those are the coefficients for a plus b squared. What about if we have a plus b cubed? What will be the coefficients then? Well, we just figured out here that p plus q cubed looks kind of like that. So a plus b cubed would simply be, instead of p's, you would put a's. Instead of q's, you would put b's. So you would get that, okay? And then the coefficients for this are going to be 1, 3, 3, 1. 1, 3, 3, 1. Okay. Next page. Use the pattern to fill in the missing numbers in Pascal's triangle. Okay, so I'm sure you've seen Pascal's triangle before. Pascal's triangle, you could find the next row of numbers by adding up the two numbers above it. So like, for example, 3 plus 3 is 6, 3 plus 1 is 4, 1 plus 0 is 1, 1 plus 4 is 5, 4 plus 6 is 10. Another thing you notice about Pascal's triangle is that it's symmetrical. So once you find half of it, do you see how it's symmetrical about this axis? So you really only have to find half of it. All the side ones are 1. Then 1 plus 5 is 6, 1 plus 6 is 7, 1 plus 7 is 8. You see a pattern with this 1, 2, and we could just reflect that. But do you see how it just grows by 1 each time? Now, the middle ones are the only challenge here, and the further you go down, the larger the middle gets. 20, 15, 21, this would be 21 too. 15 plus 20 is 35, 35, 35 is 70, 21 plus 7 is 28, this would be 28 also. 21 plus 35 is 56. See, I don't really recognize this 8 one. Wow, 28 plus 8 is 36, so 36, 36. Now I'm going to start using my calculator. 28 plus 56 is something 4, maybe it's 94. 28 plus 56, 84. This is 84. 56 plus 70 is 126. Okay. And you notice that these two series here, we have 1, 3, 3, 1. And 1, 2, 1 here. Do you see them here? 1, 2, 1, 1, 3, 3, 1. So actually, as we go down, we can pick up new coefficients for binomial polynomials. Okay, binomial cubed or to the 4th polynomial. Okay, so using Pascal's triangle, make a prediction about what the binomial expansion of a plus b to the 4th will look like. So to the 4th, that would be this row here. So we would be looking at something like 1, 4, 6, 4, 1. Those would be the coefficients. And then what would the terms be? So like the first one, of course, is a to the 4th, right? And the last one, of course, is b to the 4th. The question is, what are the others? Well, there's a pattern here. It's a to the 4th, a cubed, a squared, a to the 1st, and then the last one is a to the 0. Remember what a to the 0 is? A to the 0 is just 1. Okay. So, and then the same, you go backwards too. B to the 4th, b to the 3rd, b squared, b to the 1st, and then the first one, b to the 0, which is 1. Okay? So do you see, at the front, I got the coefficients. 1, 4, 6, 4, 1. And then I have decreasing powers of a to the 4th, a to the 3rd, a squared, a to the 1st, a to the 0, which doesn't even show up. It's just 1. And then I have b to the 4th, b to the 3rd, b squared, b to the 1st, and b to the 0, which is 1. So you see that when you build a binomial expansion, you have three components. You have the coefficient component, which you easily get from Pascal's triangle. You have this green component, which is the first part of the term, the first part of the binomial, and you're gonna take it to the power, and you're gonna go down one power every time you go down the line. And then you got the last term b, which is the opposite. At the rightmost one, you got the highest power, and then it goes down and down until you get to the front. Okay. Now the binomial coefficient, if you have a number that's like maybe like 9 or less, then you might just use Pascal's triangle to find it. Otherwise, you might use your calculator. And the calculator can calculate the binomial coefficient, any of these numbers here, like say you wanted to figure out 84 without building Pascal's triangle, you could find it by saying, oh, it's n equals 9, and then you would use a certain r, like this would be r equals 0, r equals 1, r equals 2, r equals 3. So you would say, oh, n equals 9, r equals 3, and this should give you 84. How does it give you 84? You go to the calculator, and you're going to use this function here called n chooses r. And the way you do that is first you put in your n value, which is 9, and then you go into math, and then you go to PRB. You see n chooses r, and then you say r equals 3, and we should get 84. There we go, 84. See? So you can get any number of Pascal's triangle, especially if you're getting something with a really high order. Maybe you're going to do this instead of building Pascal's triangle. Okay, so the it could be written like this, it could be written like this, it could be written like this. Alright, so those are the three ways to write n chooses r, which is basically the number of ways you can choose r elements out of a list of n elements. Alright, so basically this is like stating formally what we just color-coded in here. There's the blue coefficient, which you get from here. There is the A term, which is the green one, steadily goes down. There's the B term, which starts on the right and steadily goes down as it goes to the left. So those are the three components you need to make a binomial expansion, and believe it or not, that's pretty much all there is in this chapter.